Hello. This video is the first in the series on integral calculus, and in this video I'll be discussing some very introductory and high-level ideas about what an integral is, how we can visualize it, and what it's important for, why we actually study integral calculus. Differential calculus is about rates of change. We are typically starting with some quantity or function, and from that we want to know the rate at which it's changing. So in integral calculus we actually go in the other direction. We know something about the way a quantity is changing. We know it's changing and we know something about its rate of change. From that we want to go back and calculate the total amount of change, or something about the original quantity that was changing. So it's integral calculus moves in the opposite direction from differential calculus. So given a rate of change of a function, we want to find the total change in the function. To put in some notation, if we have a function f of t, and we want to know how much f changes between t equals a and t equals b, and what we have is not actually the function f of t itself, but the rate of change of f of t. So a good physical example that I like is suppose we have water flowing in a pipe. The water flows through the pipe, and we would like to know what is the total volume that flows between two particular times. But to understand how much volume is there, what we have to work with is a gauge that sits on the side of the pipe and measures the rate of flow. And this is actually a fairly typical situation. We have a gauge that measures in cubic meters per second how much of the water flows through the pipe. And from that rate of change, we would like to go to the total change. How much is the full volume of water that actually flows through the pipe? This is important because when we build models, we are often building those models from some assumption or some knowledge of the rate of change of some quantity. We know something about the derivative of what we actually want to study, and from that we would like to go back to the original quantity that we wanted to study in the first place. So differential equations, by definition, are models based on rates of change, and from those rates of change we would like to go back to the original functions. Now there's a second version which is really embedded in the first. Suppose we have a function g of t, and we want to find another function, capital F of t, so that the derivative of capital F of t is g of t. So here we are supposing we're given g of t, and it is the rate of change of f, and we're trying to find f. That makes f an antiderivative of g of t, and the antiderivative measures the total change. So it's by finding this antiderivative that we'll be able to go back to our original quantity, starting only with the rate at which it was changing. That makes integral calculus into a wild and general hunt for antiderivatives. And many weeks of your introductory integral calculus course will be devoted to techniques for finding antiderivatives. The third version of what an integral is geometric. Suppose we plot the graph of y equals f of x. It's the blue curve here. And we look at the area of the region under that blue curve and between the lines x equals a and x equals b and the x-axis. So it's this enclosed area right here. One of the ways we can calculate this area is by taking the integral of f of x between a and b. So we treat this as the f of x as the rate of change of the area, and by integrating it we get the area under the curve. This is another way of saying this is that the area under a graph is an antiderivative of the function itself. To see why that works, you have to imagine this right-hand point, x equals b, actually changing, and as it changes in an infinitesimal way, how much does the area change? And if we were to write out the rate of change of the area, we would find that it was this infinitesimal change times the function value itself. So that's why this function becomes the rate of change of the area underneath. To summarize, the integral of a rate of change is the total change. The integral can be calculated with an antiderivative, and that is what we will see as the main substance of what's called the fundamental theorem of calculus. And the integral of a function is the area under the graph of the function and above the axis between the boundaries. Those are three ways that we can look at an integral. And the importance of being able to integrate is that it allows us to solve differential equations, in other words, to penetrate into the meaning behind models that are built with differential equations.